Hello. Okay, so today or this section is the aldehydes and ketones and the enols and enolates. So we will go through those. So this first reaction, this is an old one. It's the anti-Markovnikov addition of alcohol, uh, water, So we have our ring, and then we have our alcohol here. So there's our anti-Markovnikov. And this is all one step, right? And then our, one and two, but it's all done at the same, within the same reaction here. And then our third step, I'm just going to write number 3. And we're oxidizing this. So we end up with an aldehyde, right? So this is just our aldehyde synthesis. On B, we have a multiple step reaction here as well. So this is one equivalent of this. And so remember that we want to protect, in this case, we're going to protect our aldehydes because aldehydes are more reactive. So what we end up with here is we still have our ketone on this 5-membered, oof, my 5-membered rings never look pretty, sorry. 5-membered ring here. And H, and then now we can make our new carbon-carbon bond with our Grignard reagent. So what we do here is we still have our 5-carbon ring and our protected, and then what we have is we have our O, and then GBR with our methyl, right? And then we do our acid workup step, and that will both kick off our Grignard and as well as give us our aldehyde back. So do this. And then we have our alcohol here. Okay. And this next one here, NaNH2, this is a strong base, right? So, and really we're just making another carbon-carbon bond, right? So, with this one here, we are turning this into 2, 3. And then we have this, right? So then this is able to react here, this here, right? So now we've made our new carbon-carbon bond. Again, a pentane. I'm always horrible at drawing, and make sure we don't lose any carbons along the way. And our oxygen. Yeah, and then we'll do our acid workup step. Right. Which will leave us with our alcohol and 1, 2, 3. There. And so this could be either H2O or H3O plus, either one, but all we're doing is just protonating here. So next we have this is predict our reagents. So with this one, what we have is we have our alkenes here. That nothing's changing here. The only thing that's really going on is we're going from a ketone to an aldehyde. I mean, an alcohol, excuse me, a ketone to an alcohol. So there's a couple ways that we know how to do that, right? but NABH4 and some sort of like CH3OH, right? This will do NABH4 will only do aldehydes and ketones. Remember, our other option that we can do would also be our lithium aluminum hydride, which would be ALH4. And then our acid workup step, right? And this one will also do esters as well. So ketones, aldehydes, and esters, right? So in this next reaction in E, we have, we're basically making a ring, right? And so something that you guys are seeing a lot in this chapter are either these hydrolysis reactions or making of an acetal or a hemiacetal. So with this one, basically what we have is we have our Lewis base, and what will happen is this hydrogen will come and pop on here, which will turn this positive so that we have something to react to on this side. And then what ends up happening is we get, if we count our carbons real quick, so 1, 2, 3, actually I should have done, because the oxygen is a part of it, right? So 1, 2, 3, 4, 5, 6. Okay, so we have a 6-membered ring with an oxygen on it. So I'm just going to throw oxygen here, and then 1, 2, 3, 4, 5, 6. And then attached to the 6th, we also have our oxygen. We have our OH, and then we also have our methyl or tail right here. Hi, Alicia, how are you?
Hi, Sarah.
Hey, I just started recording, so that way. So I didn't get too far just into this reactions a little bit here. These are just like predict your products or predict your reagents. But yeah, these are I was just doing this acetal or hemiacetal reaction here. So making a ring. And something that was actually really helpful, no, I meant to do this in the beginning, but is that we have like these reactions here for our hydration reactions. We have either basic conditions where we have like our ketone, and we have our basic, right, coming in and attacking here, and that's what gives us, let's just say, I'm just put my O here so I make space for myself, an OH, because this will go up here. And then we will have this come on here, negative, we'll protonate there, and that's what will give us this as well. Right. Versus our acidic conditions, so basic conditions attack directly, whereas our acidic conditions have to protonate first. So oops, wrong way. Well, I guess if I do it like this. Anyway, so then that's how we get this over here. And then to come in here, these will come up here. And that's what would give us this. And then we have another hydrogen. This is our plus OH, right? And then we have another hydrogen that comes in. Oh, because this has a hydrogen here. So we have another water molecule that comes in that deprotonates, and that's what gives us. And then, like any good catalyst, right, it comes back. So these are some ways to make the acetal in your basic or acidic reactions. Your base catalyzed is only going to do a hemiacetal, and your acid can make a full acetal, right? So, oh, this is supposed to be OR. Sorry, not OH, this is supposed to be OR. Whoops. Whatever. Anyway, yes, so, and then also as far as with ketones versus aldehydes, and I started to say this before, but ketones are more steric hindrance, ketones versus aldehydes. So aldehydes are, I should do this, more reactive, right? So that's why we have to protect. Typically it's going to be our aldehydes. So, and the last little thing to think about as we go along, primary amines make an imine, and secondary amines make an N-amine. Right. So just some little notes to think about as we're going along. So yeah, so when we get, so now like, again, these are like our hydrolysis reactions, right? So whenever we see this, obviously we know this is, right, acidic, where you know, we're going from an acetal. So we have this C R R, right? And then we have O R, right? This is like our, this is what an acetal looks like, right? So this is our C, and there's our OR, and then R and R, right? So we're going from an acetal, we're doing hydrolysis of an acetal. So basically when it goes all the way through like this, we're just going to end up with a ketone. So we cut it. Both of these will come off. We see this hydrolysis there, and you just will end up with a ketone in that same spot. So some of these like predictive products can be like pretty simple. And then, you know, plus you would have your two, right? You don't have to write this, but right, HOCH3. That's what's coming off here, right? And so here's our water. So we've got O, H, and H, right? So that's our hydrolysis. And you'll see, like, as we go along into these, some of these reactions, like there's some tricks, especially if you don't have to show mechanism, to be able to just predict the product pretty quickly. So I'll show you that. Again, another hydrolysis reaction here, but this time it's a hemiacetal. So remember we have this H here. And what we're going to do is we're going to break the OR bond. And what we end up with, if you counter carbons, which I always suggest doing, right, is we have 1, 2, 3, 4, and then the OH here. Oh, whoops, that actually becomes our aldehyde, sorry. There we go. And then that becomes our aldehyde there. So yeah, so we end up with that alcohol and aldehyde.
So for that,
Yeah.
when H3O is our reagent, Is that
Mhm.
like a hint that we should be splitting that bond?
Yeah, exactly. Yeah. So when you're looking at these acetals or hemiacetals, when you have H3O, it's a hydrolysis reaction versus like H plus here was like we're making the acetal or hemiacetal, but here we're starting with it. So this one we started with an acetal and this one we started with a hemiacetal, right?
Yeah.
Um, so yeah, so you're gonna break that bond between this O and the carbon here, this carbon right there. Um, not the bond between the O and the alcohol. So yeah. Yep, that's a that would I'd say be, look for the bond between the just the O and the carbon, not
Okay.
the alcohol. Yeah. You still have your alcohol. Your alcohol will turn into your ketone. Or I'm sorry, no, your ketone, your aldehyde, because it's the first degree alcohol, so it turns into an aldehyde. Um, So yeah, and then if you can always like redraw it out if you wanted to. You could have your do right if you wanted to make it look more presentable, right? But these are both the same. These are the same. But this one is just looks prettier, as they say, right? What else do we have? Okay, yeah. So this is what I was talking about before with the imines versus enamines. Um, so your nitrogen is your nucleophile, right? So we have, in this case, we have a first degree, right? We have a first degree amine. And so, the really short, quick and dirty way is you're basically, right, replacing your O with your N, but that's not exactly what's happening. You're actually, the N is coming in from the other side, the O is leaving, and then it looks like it's replaced, right? But if you wanted to just think of it in a quick and dirty way. Um, so what ends up happening here is we are literally just, it's the same kind of setup, but instead of your O, it's the N, and then just make sure to have your ethyl group on there. So we have 1 and 2, right? So, but if this is like a projected product thing, very simple like this, you also don't have to add that, but you can, because this is a part of the reaction, right? As you end up with water on the other side of it. So, and same thing in this next reaction as well. So it's again, literally kind of the same thing, except just remember that when you have the second degree, right? See, we have a second degree amine, you end up with an N-amine. And instead of having the double bond directly on the N, it's actually off the same carbon, but it's off that same carbon. So that's the only difference here. And then you'll still have your ethyl groups there. So very simple kind of predict the product type stuff. So just make sure that you still are, you have your base here, and that you're just adding the correct amount of carbons in with whatever's coming with that nitrogen. So nothing too crazy. And then these are just the opposite, right? These are all our hydrolysis reactions, right? Again, we're seeing this H3O plus. So, and that just means that, now we're adding water across it, right? Or we're like, we're hydrolyzing this. So what happens is this first one, this is, again, we know that this is a primary, right? An imine. We have the double bond connected directly to the nitrogen. We just see this one. So this is a primary. So what ends up happening is we have same, again, same structure, oxygen in its place, so to speak, right? And then we also have, now we have to add we have our CH3, so let's not forget about that. That's this one right here, right? This is our CH3. And then we're just adding hydrogen across that nitrogen, right? 1, 2, 3, right? So we have our oxygen and then our 1, 2, 3 hydrogen that we've added across this. But in nature, it really wouldn't stay like this. This is supposed to be, plus is supposed to be on this end. Sorry about that. In nature, it would end up being the proton would go away, and what you'd end up having is just, that's actually what you would see. But, you know, for conversation's sake, for this reactions mechanism, you could just, or predictor products, you can write it like this. So the same thing's going to happen with this one too as well, right? So in this case, we have an N-amine, right? So this one we have an imine, and in this one we have an N-amine, right? And again, this hydrolysis reaction. So we have our 1, 2, 3, 4, 5, right? That's this right here. And then it's going to go on this center carbon here, third carbon here. But the oxygen is double bonded rather than the carbon on this side. And then, so of course we have to replace our hydrogens there, right? So we see that. And then with our amine group, whoops, let's do this, and it always looks so funny. Okay, so then with our amine group, there's our two methyls, right? And then we're just literally just adding our hydrogens on here. So nothing crazy. Yeah, there's already a hydrogen here, just to specify. There's already a hydrogen here, so we've added 1, 2, 3, and then our O. Yeah, and then same thing with this as well, right? So this is our imine, right? This is an imine. We have that double bond directly on the nitrogen. It's a single, excuse me, a primary, right? So we just start off with our N. We know we're going to break this bond. That's what the reaction really is like we're actually like breaking that bond and then forming a new one. But it just kind of looks like we're replacing one for the other. So, but in the actual mechanism, you are completely breaking that bond. So anyway, so we have that nitrogen, and then we have, let me see, 1, 2, 3. Sometimes it's just helpful to draw it out as it was. So that you don't lose track of anything. And then our oxygen is going to come over here. And then we just make sure that we have 1, 2, 3, right? But you could also 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And then yeah. And then NH3. Right? You could also do this. Yeah. And then these last two, these, you know, this is a basic condition, right? So this is basic. So what ends up happening with this is with N2H4, we're just removing a ketone or an aldehyde. So it's just a remove ketone aldehyde. That's all we're doing here. Yeah, so nothing else really changes. 1, 2, 3, 4. And then we have, oops, it's supposed to be an O. And then, you know, this is where you don't have to draw these on, but that's what it would look like. So it's just a protecting, you know, your protecting group, right? This is what your protecting group looks like. And the only difference really is like another option that you could use would be, this is, again, like I said, this is your basic condition, but an acidic condition would be your zinc, HCl, right? This is H because you have to acidic condition. But this would also remove the ring. So remove ring, right? So you would literally just end up with, you know, hydrogens here. So it just depends on what kind of, these types of things are important for when you're doing synthesis. So it really just depends on what kind of product you want to have in the end. So N2 H4 is just going to remove that ketone or aldehyde there. So it's not going to mess with the ring at all. And then lastly, we just have this one equivalent of LDA. And so what we see here, this is a strong base, right? A strong base. So, you know, we've got these hydrogens here. right? You've got these hydrogens here. So what ends up happening is we take one of those hydrogens away. What we have is we end up with this. And then that's able to, you know, and then we have resonance. Let me just, so yeah, so then we have this resonance structure. Whoops, let me keep everything kind of the same color here. Boop, boop, boop. That's able to there we go. There. And then this is able to react with our number 2 here. So and so then what we see is this comes in here, this goes down here, and what we end up with is our running out of space. Right. So we have our double bonded oxygen, then we have, this is a hydrogen here, our methyl and our oxygen here as well. And then we do our acid workup step, H3O plus, so that we can protonate. And our final product of what we end up with is methyl, methyl. And then this would be our H, but again, you don't have to necessarily draw that on there. So, so yeah, just a strong base, you know, protonates one of these enolizable hydrogens, and then we have that reaction, and then we just have to protonate. So this should actually say H3O plus. Then we just have to protonate to make it all stable and everything. So those are just some reviews on some things that you guys have seen so far. And then we have these predict the major product and practice mechanism stuff. So do you remember what the difference between like an aldehyde and a equation? I mean, an aldehyde, an aldol, and equation. Do you remember the difference?
I think one of them is like, it has to do with acid and bases, right?
So one
And
of
also
them,
like
yeah, go ahead.
the like enolates and enol anions too, with
Yes.
the acid catalyst and base catalyst.
Yeah, so okay, so with this one, right? So equation has some sort of ester functional group on it, right? And so we see that here, right? We see this ester functional group here. Let me just erase this. So we see this ester functional group, and what's going to end up happening is it's going to leave, we're going to have something leaving as an alcohol, right? As opposed to aldols leave as an H2O, right? So we actually see like the water leaving as opposed to just the alcohol. So yeah, so we have this basic reaction here, right? Versus, you know, here we just have this, our proton, right? So acidic conditions, but yeah, so we have this initial basic reaction here with our equation. So the mechanism for this really is, so we have to like, so with, let's just say A and B, right? So we need to see like, is there any enolizable protons, right? So with this, with A, right, we have 3 of them right here, you know? So and on B we don't have any. So there's no protons here, no protons here, right? And we do have some on this side. So we know that it's gonna start here. Whoops. We know it's got to start on this side. So And it's going to start with one of these hydrogens. And so we're going to take our base. Lewis base, bronze to base, right? And we protonate that, and then this will go here. And so then what we end up happening is we have, I never have enough room for anything, even when I try to make room. So that's really, it's not supposed to, whoops. They're supposed to go like here. Okay, so this, and then we have this here, right? And with this, we have our resonance, right? Our old friend resonance. Right, and so then we're able to react with, and I'm just going to flip B around so that we have OET, O, and I'm just going to write phenyl, right? So I'm all about that shorthand. And so what we have here is that this is coming in right here. And then what's happening is then we have this whole structure. I'm trying to draw it down here. So we have this 1, and then 2, and then we have our phenyl, and we have our OET, and we have our oxygen. Ooh. Don't lose an atom here, I'm telling you. And then what happens is this comes down here, and these come over here, right? Like any good catalyst, we get to regenerate that. And then so we end up with, right, our, let's see, oxygen, and then this other oxygen here, and our phenyl here. But we're still going to have that reaction happening on these hydrogens, right? Because we can't necessarily stop that from happening. So we're going to see these OETs here come in and take this hydrogen. And then what we end up getting is, boop, boop, boop. Let me see. Whoopsies. And then phenyl and oxygen. Oh, whoops. This here, but then we have this here. And then that's when we have, this is when we do our acid workup step. So we have our H3Os. Right. And that's when we get our acid workup step, which leaves us with our final product. My cramped little space here. 2, 3, 4. Right. And phenyl. Right. So that's how we end up with that. And I'm going to show you a trick. After I'm done this next one, I'm going to show you a trick for like, if you have to do mechanisms, and obviously you have to do mechanisms, but if it's a predict the product thing, which sometimes you might get, there's a much easier way of doing these. But just for the sake of mechanism. And then so we have to look at the same thing with this. So with this one, obviously we have an aldol, right? So then we have to look at, okay, well, where do we have enolizable hydrogens? So on our first one, we obviously don't have any, right? But on our second one here, we have 2. We have one here and we have one here. So, the short and dirty way of doing this is if you know that this, so this is an aldol, which means that H2O leaves, right? So in this case, this has to be your oxygen, and these have to be your enolizable, your hydrogens, right? So if you draw your molecules, have you seen this yet? If you draw your molecules like this, and you have your 2 hydrogen here, and you draw your other molecule like this, and you've got phenyl and phenyl. Okay, you know water's leaving. Water's leaving right there. And then so you need to connect this carbon here and this carbon here. Those are the 2 that are going to connect, right? So what you're going to end up having, excuse me, is because we had a double bond here, right? So we have to maintain our double bond. Oops, phenyl and phenyl, right? So that's what your product looks like. A lot easier, a lot easier when you do it like this, right? And you can do the same thing with your equation. So it's the same thing, but just remember that you actually have just an OET, like an alcohol leaving. So just as like a quick down and dirty way to do these is it would be the same thing as like, you have your OET has to leave, right? And then a hydrogen has to leave of some sort. So if I do my phenyl and let me see, I have my OET here. And then I'm just going to flip I'm going to flip A around so that I have hydrogen, 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 and then I have 1, 2, and then, right, we're all in agreement that that's the same thing, hopefully. And then so this is supposed to be a T, OET, and this is an H. So same thing, right? It's literally just the same thing, is like you just find your OET and find your H, and then you're going to make that bond. And that's what we see here at the end. Where is it? Right here. That's what we see here, right? So, so here's that bond right there, right? Where those taking the place of where that OA2 and H is. Does that make sense? So if it's not a mechanism thing, it's kind of a simple predict the product situation. As long as you know equation, it's going to be leaving as an alcohol, aldol, it's going to be leaving as water. And then you can kind of you can make that happen a lot quicker. So hopefully that'll save you some time.
That makes sense.
Cool. Hopefully that'll save you some time. Enolizable hydrogens. How many do we have? A, B, and C. Count them. Tell me.
3 for A.
Mm-hmm. How many on B?
Wait, what?
How many on B?
1.
Mm-hmm. And C?
And then 0 on C.
Yeah, exactly. Yep. Exactly. Okay, these ones actually really aren't that bad, to be honest. It's a lot of just, has she said if you can use the plus H plus minus H plus? Have they said that you can use that notation yet, hopefully?
They said that in like the homework
video.
questions, and then she mentioned it today on office hours, but like there wasn't really an answer on like what to do for an exam. Like if we could use it or not, because some homework questions were like you can use the H plus and the H minus, and then other ones were like you can't use it. But I think it just depended on the question.
Oh, okay, that's fun. Okay, well, that's all right. Well, I'm gonna use H plus and plus and minus because it's a lot easier. Yeah. I'm sure on the exams for mechanisms they will, because otherwise it's kind of, I don't know, it's kind of a pain in the butt. Yeah, so with this, obviously we're going, you know, from a ketone to an imine, right? And we have, this is our primary, right? And we have this H plus here. So in order to go from one to the other, we obviously have to remove the oxygen and add the nitrogen, right? But it all has to, it all has to go step by step by step, right? And so that's kind of what this like plus H plus minus H plus stuff is, right? So in order to remove an oxygen, obviously we have to make it a good leaving group, right? And so in order to make it a good leaving group, we have to protonate it. So we add the oxygen, add the nitrogen, add the nitrogen, add the hydrogen, what am I saying? Sheesh. And then our nucleophile is gonna come in here, right? And we're gonna see that attack here and push these up here. And then what we see is NH here, and right, and then we have our minus H plus, right? So OH. Okay, so we've stabilized that. Now we need to make oxygen actually go away. So we add another hydrogen to actually make it a good leaving group, right? So then these go here, water says bye-bye. And then what we have is we have this resonance of H, and then we have boop, boop, boop. Did I miss one? No, okay. Whenever I flip my structure, I'm like, wait, did I do this right? Okay, so then H and H. Okay, and we've got the plus here. Okay, and so then all we need to do is take away a proton, right? And then we end up with our imine. Not to be confused with amine. Yeah, did I miss anything? No. So they're it's just honestly these ones are just like a lot of work, but they're not really that hard, which is the good news. So and then we have the same thing happening here, right? We're in this acidic conditions. We just need to add OET, right? So in this case, again, we have to protonate first, right? So we have to protonate first. And don't forget, right? Your Lewis acid, Bronsted acid, Lewis base, Bronsted base. I didn't do that for this stuff up here. Please don't forget, right? Lewis acid, Lewis base. So just, don't forget those. I don't always do them, but it's good practice just to do them. So again, we have the same thing here, right? So we have OH, and then we have our OET that's going to come in here. Yes, feel free. Don't raise your hand. Just speak up because I won't always be looking right at my computer. So please definitely hop in, Jacob.
Okay. I was going to ask about the catalyst. Does that indicate whether we protonate or deprotonate in a reaction?
So your catalyst is always going to be regenerated. So that's the biggest thing about that. In this case, you're going
What do
to
you mean?
a catalyst is always regenerated. So you always end up with, like in this case, like a catalyst just helps the reaction along, right? So in this case, it's offering up its proton to get the reaction started, because as it is, there's nothing really going to happen. Like this and this are kind of okay as they are. Like they don't have to react. You know what I mean? So that's what this catalyst is for, is it's basically creating a condition to allow a reaction to start. But it's not consumed in the reaction. So it's not
Okay.
consumed by the reaction. So you'll always end up with whatever your catalyst is, right? In this case, we have HCl, right? But HCl basically it's offering up that proton here. That's what's getting this kind of getting the party started. But in these notations, yes, the plus H plus minus H plus, right? That's basically what this kind of shorthand is, so that you don't have to show every single little thing that goes on. And same thing with this, right?
Oh,
Yeah, so in this case, like, right, we just have H plus catalyst, right? But it's kind of the same thing. So when that's why I was asking, like, is it okay that you
okay.
guys do this? The plus H plus minus, because you're basically, otherwise what you'd be doing is you'd be doing this every time. And then if you wanted to take one away, then you'd have this,
Then you'd have to like
here. Yeah.
do it every single time. Just
Yeah, exactly.
so it's just to save a step in writing the reaction.
Basically scientists are lazy. Chemists are lazy, physicists are lazy,
Perfect for me
biologists
then.
are lazy. We're all lazy, all of us. Every single class that I've ever been in a science class is like, technically this is what happens, but this is actually what we write because we're lazy, right? So,
Yep.
yes. So that's all that means.
Okay.
Yeah. So yes, so we have this a plus H plus, right? And so we see that here. So that's what protonates this. Our oxygen, like I said, to get that party started, right? So then our OET can come in and actually have a reaction with the molecule. And then we see, okay, don't lose track of what you have, right? And then we have, let me see, 1, 2. Oh, I'm like, what is going on with this molecule? That's why. There we go. Sheesh. Okay, and then O, E, T, right? And then we have hydrogen plus, right? Okay. So now we obviously have to get rid of Lewis acid, Bronsted acid, and our Lewis base, Bronsted base is going to be another water equivalent, right? Molecule here that's going to come in and deprotonate that, which you could say is equivalent to like negative H plus, right? Like that, it's equivalent, right? But just to show you the mechanism, because I think that's what this question asked for. So then we have OET, and then we have, now we need to get rid of, we want to get rid of this. So we're going to H plus, right? But we could, if we wanted to not be lazy, we could write HCl, right? Or whatever, right? But we're just going to write H plus. So come in, take one of these. That makes us a good leaving group. So now we have this here, OET, and then we have this water, essentially, right? I'm shorthanding this, which is going to leave. And then what we have is we have this resonance structure of running out of room. Oh, wait, do I have more room? No, of course you don't. So what we have is we have this resonance structure of, I'm just going to do this, OET, and we have a plus here, right? Plus there. And so then our resonance is here, OET, right? And then that's a resonance, but we have another OET that's going to come in here, and it's going to attack here, and then you're going to get, woo, OET, right? That's this right here, OET, and O, E, T, and H. And then we have to have another. This is why these get like kind of long and drawn out, right? So we have another one here that will take this and deprotonate that and pull that here, which will end up giving us this here. Sorry, guys. I write too big. That's my problem. But yeah, so this is your Lewis base, Bronsted base. This is your Lewis acid, Bronsted acid. There we go. Yeah, so that's that mechanism. I think the OET ones are the worst because they're like just so much, you know. And then yeah, so then C is like literally just the opposite of this, right? So we have this HCl catalyst here, and here we're just, you know, we're oppositing it, right? So we're just doing literally the direct opposite of this. So what we need to do is we need to break this, and we need to break this, right? So come in with this H3O. And this will protonate. This will protonate here. And then what you'll end up with is you'll have, let me see. I don't want to like not have a ton of space here. Let me see. So OET, OETH. Okay. And then this will leave. And then you'll have OET. And then this resonance. So that we can have this oxygen come in and react. Then what we have is we have O, H, H, and this, we have O, E, T, oops, E, T, sheesh. And then we have another, oops, water come in. So remember, there's just like water and H3OI, and like everything's just swirling around in all this space, right? So there's millions of them, billions, trillions, Avogadro's number times many of them. Anyway, we have our alcohol here. We have our O ET here. And then this is going to pick up a proton from here. See, I'm still running out of room no matter what I do. I'm going to come this way a little bit. Let's see. This is going to go here. And then what happens is this gets kicked off, right? So I'm going to come this way just so I have some space. So then I have plus OH, and the resonance to this is this, right? That's the resonance to this. Sorry, I know I'm drawing over this. And then we have this water molecule that comes in and deprotonates that. And so then we end up with our final product, right? So that's the mechanism, that one. So we're literally just going the opposite direction. So same, but opposite, right? And then we'll see the same thing again too in this one as well. It's pretty much the same thing as I think A. Yeah. So we're literally just doing the same thing but opposite with A as well. So gosh, what a pain in the butt these are. Okay. All right, so let's see. Let's do plus H plus. So then we end up with OH and plus, and then so these are going to go here. So that NH2 can come here. And then what we end up having is boop, boop, boo, N. I'm just going to do this with our H2 here and our OH here. So now that is happy the way it is, but this one is not happy because this is positive, right? So then 1, 2, 3, and then this just becomes NH plus the ethyl. And then we want to get rid of this. So we add a hydrogen, add H plus. So then we end up getting this, which will knock off, and we have this, right? Which ends up giving us this resonance structure here of, because that left, we have that cation there, and then we have N with this H, right? So that's that same structure, but we have this resonance here that we need, right, ultimately. And the H, I'm just trying not to run out of room, right? And this is positive. So then what ends up happening is we do from this structure minus H plus, and that's how we end up with this here, right? So we see mechanism versus we see just H plus minus H plus. Obviously this plus H plus minus H plus is a lot quicker, a lot easier than having to do all this mechanism stuff. So a lot of it's just really going to depend on what the question asks for. And as long as you can kind of just go through and, you know, make these, you know, heuristics as they call them, right? But like we know, right, with this here, like we have to protonate that in order to make it a good leaving group. And then when it leaves, you know, we have these resonance structures here that allows for this other O to come on, because remember that, excuse me, this O here is not these O's here. So that O actually comes from this here. So those are two completely different O's. So when you see stuff like this, like these both have to leave. And same thing in this case, right? Well, this one's a little bit easier to see because we're changing, right? We're going from an O to an N. But sometimes it can be a little bit difficult to imagine. So yeah. And then what? Show how you would synthesize these target compounds. Oh, these are my favorite. So some stuff that we're doing here, right, is we have to add a CH3, right? So we've added a CH3, and then we've turned this alcohol into an imine, right? An imine, right? So those are the two things that we've done. And that's the thing about this chapter. So we've added this here, and then we've turned this alcohol into this amine, right? So that's the thing about this chapter is how do you make something, how do you make multiple functional groups without necessarily getting rid of or changing or exchanging the ones that you have? So in this case, we have an alcohol on both the beginning, a second degree alcohol in the same spot at the beginning and the end. And so that's some things that we want to watch out for, right? So obviously we have to use probably, right, some sort of Grignard reagent. That's why we learned that. It's pretty useful. So when it comes to you know, making this molecule at the very least, you know, just according to like some of these last reactions that we just did, obviously we have to add some sort of we have to add our imine, right? So we have this N12. Okay, so we have to add some sort of imine, and then we just would have our H plus catalyst, right? Just something like that. So that's how we would get here, right? So prior to that, in order to get that, whoops, I don't know why 5-ring structures Oh, pentene, cyclopentane always is the death of me. Okay. Let's see. OH. And then so before that, obviously we had to have, right? We just did all this, right? So this isn't a far stretch. Like to go from here to here shouldn't be a far stretch because we literally just did all of this. This one right here. Right. So we're just applying that those same principles. So yeah, so we haven't done anything too crazy yet. So, but prior to this, you know, we have this alcohol here. And so we have to be able to attach this CH3, this methyl group, right? But with a Grignard reagent, if we have our alcohol, it's going to we're going to end up reacting with it. So we have to have some sort. We have to protect. I mean, our alcohol, our aldehyde, right? So we have to be able to protect our aldehyde as well, because aldehydes are extremely reactive, right, with Grignard reagents, and we know this. So in the beginning, in order to go from here to here, right, we have to convert somehow, right? And so first we have to do some sort of like oxidation reaction, right? Because we need to make this ketone. We have to make a ketone, an aldehyde, excuse me. We have to make an aldehyde. So we have to do some sort of oxidizing reaction in order to make that happen. So the best, you know, reagent that we kind of know for that would be our PCC with some sort of like CH2Cl2, right? And this is just like a simple oxidizing reagent. So we have this here. We have that here, right? And so remember, oxidizing reagents, all they do is just add more bonds to oxygen, right? And then, but like I was saying, is we have to protect in order to keep this. Oops, got my hydrogen. You guys didn't say anything. In order to keep this, we have to, right? So let me back up a little bit. In order to put this methyl here, we're using a Grignard reagent, right? That's one of the best and easy ways to do that. But in order to do that, we have to have this, right? We have to have this, right? We have to have this type of area for it to come in on. And so it's not going to do it on this alcohol alone. So that means we have to turn this alcohol into a ketone in order to get that space to react, right? Because remember, with the Grignard reagent, oddly enough, that carbon on the Grignard reagent is actually pretty negative, which is one of the few that's actually negative, right? So in order to do that, we have to make that space for it to go on. But like an alcohol, you can't, it's not going to add anything there, right? So there's nothing for it to add to. So we have to make that double bond. So that's why we oxidize it first, right? But then now that we've oxidized this, we're going to oxidize everything, which is okay. That's what we want. We need this aldehyde to be able to put our amine on there, right? But if we do our Grignard reagent, it's going to react to either or both of them, right? So we have to remember, we're doing this protecting. We have to protect the aldehyde because the aldehyde is more reactive with the Grignard reagent because there's less steric hindrance versus the ketone, right? So what do we use to protect our aldehydes, right? And we've seen this, right? And so in this case, we have to specify one equivalent, right, of, and some sort of catalyst, right? And so what that's going to do is that's going to protect our aldehyde. So again, so we have this exposed ketone, which is good. But then we have our protected aldehyde, right? And then what we want to add is a methyl, right? So we have to have CH3 and then MgBr, that's our Grignard. And so that's what we need there. So then we get to attack right here, right? So that's what'll happen. not a double bond, OMGBR methyl, and then we still have our protected group here. Well, how do we get rid of MGBR? And also, how do we take our protecting group off, right? It's that acid workup step. And so that's how we end up back with our alcohol here and how we get our aldehyde back, right? Is we take off this protecting group and we get rid of MGBR, and that's how we get our alcohol back. And then here we are, boom. We just add our amine and our primary amine to get our imine onto our group, right? I know synthesis isn't fun, guys. It's okay. It's a bane of my existence too. But does that stuff make sense? Do you guys have any questions on it?
No, it makes sense.
Okay. So when you guys see this, what do you guys think? What do you see that's different? What do we do?
The addition of the phenyl group.
Yeah, carbon-carbon bond, right? You know, is this, what do you think would be better, Grignard or some sort of like alkyne addition? What do you guys think?
I have no idea.
That's okay. Okay, so this takes us back to our alkynes chapter a little bit, right? And so we know we have this alkyne here. Remember, we had that reaction. What the heck am I spelling? Whoops. Alkyne. And so do you guys remember the NaNH2, right? Stripped the hydrogen off the end of the alkyne to make it a good reaction spot. So anyway, that's essentially what we're gonna do, right? But in order to add, so and in this case, right, if we wanted to add, so this is where we're adding something. So we have one carbon here, our phenyl group here. So that means that in order to do that, let's just look at this right here, right? So in order to do that, what's our synthetic equilibriums? Equivalents. Our synthetic equivalents are, right? We have to have this and this, right? Those are our synthetic equivalents to be able to make this reaction right here happen, right? And so, you know, some of the best ways that we know how to do that, obviously, right? There's our BR. That's phenyl, right? So yeah, so I mean, you know, this is like, you know, classic substitution reaction there. So let's see, then we go, let me erase this stuff. So yeah, so we're having this. So we need to have some sort of, right? Some sort of adding of our, right? This is what we're going to need in order to get that phenyl group on there, right? But to get there, right, we still have to do some sort of protecting of the ketones. So that way we're not reacting on that end, right? So in order to do that, we have to put our, to protect the ketones. So we know that, just let me see, one, if this is here, so 1, 2, 1, 2, let me see, 1, 2, 3, 4, there we go. Sheesh. Yeah. So we have to protect the ketones. So, okay, so yeah, so we have, so in order to get this on here, right? So then this would just be our acid workup step, right? Because that's what gets rid of our protecting group. So to add our phenyl on there, we have to have that, like I said, our synthetic equivalent, right? So this, like this, right? And then this would be Na. And then that's how, right, Br leaves. We have this good little leaving group here, and our phenyl adds on, right? So this would just be our reagents right here. In order to get that, we need to have our NaNH2. That's what strips that hydrogen off of there, so that we have, oops, working backwards here. Let's see, that's what strips our hydrogen off of there. Make sure I don't lose my carbons. Okay, so 1, 2, 3. And then there's our hydrogen, right? That this strips off. That's why I have this here. There. Okay, not gonna lose anything. Right? Check the ketones, so nothing happens to it. Okay. So yeah, these protecting groups are just so that, so this is, you know, how you protect it, 1, and then how you get it back, 2, right? And then everything else in between, because as we see, we have this here, so we want to keep that. So everything else in between, you know, is what just gives us this new carbon-carbon bond here, right? Between here and here, this new carbon-carbon bond. Okay.
Yeah.
Cool. What else? What else? So these ones, right? Similar thing. I think this is the last one I have here. Yeah. So again, on this one, right, we have an aldehyde and we have a ketone. What have we done between these two? We've made a carbon-carbon bond, right? And we made a primary alcohol, right? So, like I said, like I've been saying, as you guys know, aldehydes are the most reactives. So those ones need protection when you're using a nucleophile or a base, right? So, because your ketones will react to any type of nucleophile or base. You know, same reason why you have to protect it here, right? Because this is a base, right? This NaNH2, yeah, is a base, and it will react with our ketone. That's why we have to protect it, right? So same, but different, right? So let's just add that on there right away. Whoops. Yeah, H plus. Okay. And we just add that on there right away. So we don't even have to think about it, right? Okay. This is CH3. Okay. There we go. Perfect. And then, and then same thing, right? We want to make that carbon-carbon bond. So we do that by using our Grignard reagent, right? So in this case, we're adding, right? We already have a methyl here and a methyl here. So in this case, we just want to add an ethyl. So literally it's just ETMGBr, right? And that's what adds that. So we still have this, and we still have this hydrogen and this phenyl group. And then we have this. But now we have ET, or to make it look more like our structure, I'm going to do it like this. And then we have O MGBR. Don't draw it like this. I'm just trying to get space. And then we do our acid workup step, right? Because we want to get rid of that stuff. So yeah. So basically with our acid workup step, what we're doing is we're getting rid of our protecting group and we're getting rid of our Grignard. So then what we end up with is we end up back with our ketone. And then let me see this. And OH. So we have our OH, we have our ethyl group, right? We've added our ethyl group. So one last thing that we have to do is we just have to turn our aldehyde into an alcohol. So and we know a couple ways to do that, right? NABH4, NABH4, and then like CH3OH, right? We could also use lithium aluminum hydride, right? Same idea. That one will also do esters. So yeah, and that's that. So yeah, that's all I have. Do you have any questions about anything?
No, I don't think so. It actually is really helpful, so thank you.
Yeah, no problem. Anytime. Definitely feel free to, if you need like, send me an email or whatever. I'm happy to answer questions or, if you're stuck on something, so don't be shy, as they say.
Thank you.
Yeah, you're welcome. Have an amazing rest of your night. Good luck. I think your exam's due tomorrow, right?
Friday, yeah.
Oh, Friday, yeah.
So I think it opens up Thursdays and it's due Friday night.
That's what it is. Yeah, that's what it is. It
Yeah.
opens tomorrow and then it's due Friday. That's what it is. Okay, yeah. Well, good luck on your exam. And it's the second to last one. So hopefully.
Yeah, we're almost done.
Yeah, you're in the home stretch.
Yeah. Thank you.
You're welcome. Have a great night.
You too.
Thanks.